Hey, this is just a quick note about our sponsor, Privado, the premier enterprise privacy platform, purpose-built to bridge the gap between privacy and engineering. Its privacy code scanning solution embeds privacy compliance and governance into the product development lifecycle and empowers privacy and security teams with unparalleled visibility of sensitive data flows and the insights to find and fix privacy vulnerabilities. You can leverage Privado's data flows, dynamic data mapping, privacy assessment automation, and real-time visibility of privacy issues. Enter the era of proactive privacy and transform privacy from business blocker to business enabler. To learn more, go to privado.ai. Hello, I am Deborah J. Farber. Welcome to the Shifting Privacy Left podcast, where we talk about embedding privacy by design and default into the engineering function to prevent privacy harms to humans and to prevent dystopia. Each week, we'll bring you unique discussions with global privacy technologists and innovators working at the bleeding edge of privacy research and emerging technologies, standards, business models, and ecosystems. Today, I'm delighted to welcome my next guest, Damien Differential, staff scientist at Tumult Labs, a startup focusing on differential privacy. Before that, he led an anonymization consulting team at Google, and he specializes in making it easy to safely anonymize data. He also earned his PhD and did his thesis at ETH Zurich and a master's degree in mathematical logic and theoretical computer science. Tumult Labs' platform makes differential privacy useful by making it easy to create innovative privacy-enabling data products that can be safely shared and used widely. And so today, we're going to be focusing our discussion on differential privacy techniques. Welcome, Damien.
Thank you, Deborah. It's a pleasure to be here.
Excellent. Okay, so first, why don't you tell us a little bit about your background? How did you get into tackling this data science privacy problem with differential privacy? And also, I just discovered that you use the name Ted, a pseudonym online. So I'd love for you to include why you do that in your answer.
Sure. So the pseudonym Ted goes back to, I think, a long time when I was first on the internet and I was looking for a pseudonym such that if you looked that up on Google, you would not find me. And then over time, I kept it and my identities become intermingled because turns out maintaining anonymity online over time is very difficult. So at some point, I just gave up. I went into differential privacy, I think a little randomly, no pun intended, when I was at Google and joined the privacy team. I noted that there was a really big disconnect between the way anonymization practices worked in industry and the way I could see computer scientists focusing on in academia, looking at the papers that were talking about the stuff. In academia, it seemed like everybody used this new fancy cool thing called differential privacy, which gives you like a bunch of cool guarantees we're going to get to later. But in industry, this technology was not used a lot, and people were still using sort of more old school techniques that I'm also going to talk probably a bit about. I was very interested in the reasons behind the disconnect, and so this is what I initially focused my PhD thesis on that I did back then. Yeah.
Oh, excellent. Well, then I would love to hear some of the reasons that you discovered through your research. Like why is there such a gap between the academia and the corporate world?
So just to give like a little context, what I mean by old school techniques or sometimes ad hoc techniques, people also use the word syntactic privacy, are techniques like removing names, removing things that look like identifiers, or only publishing statistics when there's enough people in them. And that's what people do when they want to, let's say, share sensitive data with partners without revealing information about individuals. So these techniques were born a few decades ago. And it turns out that in academia until 2010, most of the research was focusing on those, but successive researchers looked at those and found cases where they didn't work and essentially created attacks on these old school techniques and successful attacks to get individual information out of even aggregated data. So they invented this new notion called differential privacy, which was proposed in 2006, which provides sort of much stronger guarantees. But differential privacy, it makes very strong assumptions about the attacker, which is good from a formal mathematical perspective, but might not feel realistic in practice when you look at this initially. And it also feels complicated. You have to add some randomness to your data. You have to do all sorts of data transformation operations to make that possible. And the very notion of having to add noise to data was sort of scary to people, which I think was one of the main reasons why it didn't really catch up in industry, at least not initially.
So then what is the differential privacy guarantee? And then maybe how was that mismatched? How is the alignment between industry mismatched based on the true guarantee and I guess the expectation of what differential privacy, is supposed to do from a corporate perspective?
So when I started my research, what I actually set out to do is to try and look at these old school definitions and say, okay, maybe they don't work perfectly all the time and you can make theoretical attacks against them, but maybe in practical scenarios, maybe they're good enough. Maybe we can interpret their guarantees in the same language as differential privacy. What does that mean, the same language? What differential privacy tells you is that it gives you a bound on how much probabilistic information you can learn about a person by looking at the anonymized data. So let's say, for example, I have I don't know whether somebody particular in the data has a cancer diagnostic associated with their record. Initially, I have no idea about this. I'm going to give it, let's say, 50-50 odds. If I had to guess, I would maybe give you $1 and maybe get $2 if I'm right and lose my $1 if I'm wrong. What differential privacy tells you is after seeing the output of the anonymized data, after looking at the data that was published, maybe I can increase that knowledge a little bit. So instead of having, let's say, 1-to-1 odds, I'm going to have 2-to-1's odds of getting that answer right, but not more than this. So I can't gain full certainty, which is very powerful. It means I provably cannot learn anything for sure about an individual. And even better, I can quantify that. I can tell you exactly how much more I can learn. That's very strong, and that's not a property that any other privacy definition sort of gave you at the time. So I initially set out to figure out whether we could come up with the same formulation of a guarantee for old school notions under certain assumptions. Differential privacy, for example, doesn't depend what auxiliary data you use, or it assumes an attacker that is very strong and that has infinite computing power at their disposal. So these strong assumptions, maybe I would think maybe we can reduce these assumptions to get results on these old school privacy notions. What I discovered that actually the main obstacle to the wide-scale deployment of differential privacy is more along the lines of education and usability. Basically, if you make it easier to use these much stronger techniques, people will actually use them and find that it works well for their use cases. But that work of transforming theory to practice and make things usable and scalable and explainable and so on, that's sort of the hard part, and that's what we're working on right now.
Excellent. Well, thank you for that summary of kind of how you view this space and what differential privacy is. And so there's different types of differential privacy from what I understand, local versus central differential privacy. When would you use one over the other? And what are the differences between those two approaches?
Right. So central differential privacy is the model that is most deployed right now. And it essentially happens when you have one organization, we usually call that the data custodian, who has a lot of data about many people. So they have access to all of everybody's records and so on. So this happens a lot, right? Think about a government agency having records on citizens, or big tech companies having interaction data with the services and so on and so forth. And they want to publish insights about that data, statistics about that data, or even machine learning models trained on that data externally, while making sure that this does not leak information about individuals. They have all the data initially, and then they publish something about that data. That's central differential privacy because this requires to have a central point where all of the data is. Local differential privacy is a technique you can use when there is no central, you want the central aggregator to not have access to the real data. So instead, every person who will send data to the aggregator will add noise, will add some randomness on their own data. Then they will pass it to the aggregator, and then the aggregator will publish some statistics based on that. Local differential privacy has this nice thing where you make fewer trust assumptions. You don't have to trust the aggregator because the privacy guarantee applies to them. Each user is hiding their own true data from the aggregator. The problem with local differential privacy is that the amount of total noise you have to add, the total uncertainty you have to add to your data to collect statistics is much, much, much wider. So it really only works for applications where you're okay having lots of uncertainty in your data, and you really want to be able to not trust the aggregator. I think this is a common use case, and this sort of exists, but there are other techniques you can use in that context, like cryptographic techniques, in ways that sort of avoid the amount of noise. But at this stage, it's sort of, I don't know any real-world deployments using that, so it's sort of mostly research. Today, most of the big names who deploy differential privacy use the central model: Google, Microsoft, US Census Bureau, Wikimedia, etc.
Do you think that there's mostly because there's more research in that because the research is being sponsored by large organizations, or is it that it's harder to do local differential privacy? Is there just less funding for that? The central aspect.
There's theoretical limitations, as in fundamental limitations to what you can do.
Okay.
So basically, like one rule of thumb that was published in a paper by Google folks who Google also deployed, like one of the very first real-world deployment of differential privacy was actually a local differential privacy, Google Chrome. But the researchers who published this report that if you have end users, let's say like 1 million, you can at best observe behavior that at least you have a square root of n people that display that behavior. So if you have like 1 million users, you can maybe detect behavior that's common between 1,000 people, right? Square root of 1 million, but not fewer. And often you need even more people in order to get any signal out. So in many data analysis applications, that sort of fundamental limits, which is, you can prove fairly easily that you can't do better with local DP, will severely limit the range of applicable use cases. In parallel, also in the last 10 years, there's been some more research on this problem of collecting data privately. And there's other approaches to doing this rather than only adding noise locally. You can do things like multi-party computation or secure aggregation or federated learning. Like all of these sort of set of techniques can be used in that context and actually might be, like you can combine them with some central differential privacy afterwards, but it feels like more promising than for the data collection problem than local differential privacy. Central differential privacy, on the other hand, has been proven useful over and over again and is currently gaining adoption because it's like the properties that it displays are both provide strong guarantees and also are usable and useful in practice.
That's really helpful. And I know it's also, I know you can kind of mix and match different privacy enhancing technologies based on use cases. When you say stronger guarantees, it sounds also like you've got more simple deployment with more accuracy, right? Is that right? What it sounds like? So you wouldn't even use differential privacy in some cases, local differential privacy, because you have more accurate, easier to deploy privacy enhancing technologies for those use cases. Is that what I'm hearing?
By use cases, you're talking about the collection or the data sharing and publishing?
I wasn't making a distinction. Yeah. Why don't you make that
distinction? Maybe I should have started with this. Okay. So basically, central DP solves the problem of publishing or sharing data that you own, that you already have, that you're custodian of and you already like what the data is. Local differential privacy solves a different problem, which is how do you collect data in a private way? How do you get statistics about people without knowing their true answer?
Got it. Okay.
The techniques are not one or the other. It's usually the problem statement that sort of tells you whether one is a good option or whether you should use the other one.
Makes sense. So I know from your website that to ensure effective sharing of sensitive data, that Tumult Labs provides a suite of offerings to help organizations, of any size, assess, design, and deploy differentially private solutions. So I really want the audience to better understand this approach to deploying differentially private solutions. So if you're game, I'd like to list each stage and then kind of have you expound upon what some of those best practices or what's the thought process at this stage when it comes to protecting personal data. Sound good?
For sure, yeah.
Great. So first is the assess, design, and deploy, right? So first is the assess stage. What goes on in this stage?
So at this stage, what we're trying to understand is the organization we want to talk to has a data publication problem or question. They have some data that they hold and they want to share it with a somewhat untrusted third party or publish it to the world. the first step for us is to understand what is the problem that this data publication solves. Often people start out thinking, I would like to publish this data to encourage research or to allow people to derive useful insights, to add measurements or to answer that question. And we try to get to the root of what that fundamental question is. How is the data going to be used? In that process, you try to determine not just what the problem is, but also how is the solution's utility going to be quantified? Like, what will success mean in the context of that data publication? This usually, you start the discussion at a sort of high level, what problem does it solve, and you end up, the result of that process is to generate at the level of error metrics. Right? We're going to look into the difference between the data we're going to publish and the real data we would like to publish. We're going to look at how much of the data were we able to gather insights about, how much of the data was suppressed, what is the relative noise into the data release compared to the actual signal. All of these error metrics we can quantify and translate in mathematical terms. This is both useful for us, because then we know what to optimize for when we design an algorithm in the next stage, but it's also often very useful for the organization to really understand what success looks like for them, what the goal of the operation is, and what the value of the data product they are going to ship is going to be for them. Typically, the outcome of this is both an understanding by the organization of what can be done and what can be realistically done with the privacy guarantees we propose. It often includes an explanation either for them and or for the data users about the privacy guarantees they're going to get, like how what we sell is privacy technology, right? So we sell tools that allow people to publish data and still sleep well at night. So that second part is very important. We have to convince them why this data release can be made sort of safe enough for their legal, privacy, ethical requirements. And you usually produce reports, presentation, error metrics, and so on. So we can set us up for success in the next stage.
Neat. Thank you so much for that. And then the second stage would be design. So you're starting to figure out, I guess, the architecture and how you're going to design this process. So tell us about that.
That's right. So once we know what we're trying to build, once we know what we're designing for, we as experts help you or do for you write an algorithm that will generate the data that you want to generate in a differential private way. So the two things to note here is that first, everything we do in this stage is built on a general purpose differential privacy platform that we built called Tumult Analytics. That's also open source, so you can go and try and build your first differential privacy algorithm using our open source platform today if you want to. I'm sure we can have the link next to the podcast. And second, that process of designing an algorithm is a very iterative one. What often happens is a first algorithm is produced either by us as Tumult Labs experts or by the organization itself. So the engagement we have with Wikimedia, for example, Wikimedia data scientists are directly using our platform to build an algorithm. And then we run the algorithm, we evaluate the results against the error metrics defined in the previous stage. And often the very first cut of the algorithm is never good enough. So we look at where are there unacceptable utility or too much suppression, or some things are not going as well as we expected in the data. And then we iteratively optimize some parameters, revisit the total privacy protection we are providing by increasing or decreasing the privacy budget, the thing that quantifies how much probabilistic information an attacker can gain. And we iterate between this often requires sort of refining error metrics over time as you realize that there's maybe things that you hadn't thought of that actually also are important to solve that problem. And at the end of the design process, you end up with a prototype algorithm that satisfies the fitness for use requirements. That makes it so if you're releasing the data produced by this algorithm, this will actually solve the problem that you're trying to solve, and this will make your data users happy.
Makes sense. And I just want to point out to the audience too how nothing about what we've said so far has anything to do with compliance. It's just good privacy practices, preventing privacy harms, putting these practices in place to protect humans, right? So this isn't about compliance, although it can get you to regulatory compliance, right? And how you're sharing data and such. But I just wanted to throw that out there because it's just I think a really important point to underscore that privacy, like security, should just be baked into an organization and all aspects of the business, especially around protecting personal data.
I think you're completely right. And I think what we tell our customers is using gold standard techniques like differential privacy to safely release, publish, or share data, we tell them that it goes beyond compliance. But very clearly, like, part of the value proposition, right, is that it gets you to the compliance bar because it's the gold standard of these techniques.
Yes, it gets you there. But what you really want to do is unlock the value of your data so that you can use it in ways that are profitable to the company and gets you to your KPIs or whatever, or your goals, but that is privacy protective and meets the regulation. So
absolutely.
Yeah. Okay, why don't you tell us about the third stage, and that's deployment? Like, how do you help customers deploy this technology?
So deployment is once you have an algorithm to generate data, it's often not as simple as clicking a button to actually push that thing to production. Often you need to do things like document the algorithm and explain how it works and what these properties are to the people who are going to use the data.
And that is a requirement in the EU.
Yeah, right. Another aspect of deployment is if you're doing a data release that is sort of continuous over time. For example, with Wikimedia, we are releasing data every day based on the logs generated every single day. Then the initial strategy, the initial algorithm, was designed using maybe some historical data. You want to make sure that the assumptions you've made then are still holding up over time, and that there's no data drift that will make your algorithms perform worse over time. So part of deployment is to understand how that can happen and how you can catch it and detect it when that happens and how you can course correct. Finally, there's all sorts of technical support involved in actually shipping this stuff to large organizations and clusters and so on. So we have a great team of engineers who can help you through that.
Thank you for that. I really appreciate it. So some use cases around data publication, so publishing data or sharing use, are well suited to the use of differential privacy, while some are not. In fact, you wrote a really comprehensive blog post on this for Tumult Labs. And again, I'll share that in the show notes. Can you shed some light on what are good use cases for differential privacy techniques and what use cases may not be good candidates? Basically, what's the litmus test for when it's appropriate to use differential privacy?
Stay with us. We'll be right back.
Hello, loyal listeners. The Shifting Privacy Left podcast is seeking sponsors who want to help educate our growing community of privacy engineers. Position your brand in front of privacy engineers, architects, developers, researchers, and privacy tech buyers. Insert a 30 to 60 second ad like this one into every published episode of the podcast. This is dynamic content after all. Feature your new product, an upcoming conference, a sponsored special deal, endless opportunities. Email sponsorship@shiftingprivacyleft.com for more information on our sponsorship package. Okay, let's get back to our engaging privacy conversation.
Yeah, it's probably simpler than you'd expect. Essentially, differential privacy at its core, it's going to try and hide any individual contribution from the data in the end. So let's say you're doing something very simple, like counting the number of people with a certain diagnostic in your data set. A single person being added or removed to the data set, a single person can at most influence that total statistic by one, right? Because either they have this diagnostic or they don't, but the total count will not change by much because of that person's data. So all you need to do to satisfy differential privacy for these specific statistics is to add some random noise. You can imagine of like rolling a dice and adding the result to it. And the magnitude of that noise needs to cover the contribution of any given person. If that contribution is 1, you just need to add, random noise of variance or standard deviation, 1, 2, 5, 10, not a very large number if your statistics are big enough. So that's essentially the litmus test is if somebody, can the statistics that you're outputting, that you want to generate, can be significantly changed if you just change the data of one single person. If a single person can have a great influence on the result of your analysis, if it's critical that you catch changes in individual behavior in your analysis, then differential privacy is not going to work because what the algorithm is always going to try to do is to try and cover this individual contribution. Conversely,
because it's an outlier? This is a
typical example. Yes.
Okay.
So in a use case like outlier detection, if your goal is to detect the data points that are outlier in the data, then very clearly differential privacy is not going to allow you to do this well because it's designed to prevent this kind of inference about specific individuals. That litmus test, the nice thing about it is it also works the other way around. So if fundamentally the thing you want to get out of your data are global insights, statistics about the behavior of like multiple people at once, then often it's not going to cost you a lot of utility to add the noise necessary to get these very, very strong privacy guarantees. So use cases around measuring aggregates user behavior, computing statistics over medium to large groups, all of these kind of use cases typically work very well with differential privacy. One maybe exception here is, again, if the statistics are such that a single person can contribute to them, can have a very outsized influence on them. If you imagine you're in a room and you're trying to get the average salary of the people in this room, and all of a sudden Jeff Bezos enters the room, very clearly that's going to make that number go up like widely. This single person is going to have a widely large influence on the data. It's often in data analysis something you don't want to happen. When you're doing statistics, when you're doing science, you don't want your analysis to be very brittle and to depend on the value of very individual people. You want your analysis to be robust, and the results, the knowledge you're going to get from this, you don't want it to widely change if a single person has different data. So whenever you want to do something that's sort of robust in this sense, then differential privacy is going to be a great fit.
So then how can data scientists make the analysis more robust to better preserve privacy?
Well, if we go back to this average salary example, if what you want is some information about the salary of the people in a room, the average is actually not a great metric because of these outlier data points who can make your metrics widely, and the results, if you get a high result, you don't know it because you don't know whether it was because there's a single super large outlier or because the average salary of the people in the room was actually that high. So in the sense, you usually want to do something like either consider other kinds of statistics, like instead of averages using medians, which are typically a little more robust, or you can say, okay, if we have outlier data points, we're going to bound the contribution that they do. Maybe every salary above 1 million, we're just going to pretend it's 1 million. And this way, they're going to have a bounded, measurable influence, maximum influence over the data. That makes your statistics more robust, and it also typically improves both the robustness of your analysis and how well is differential privacy going to perform for this use case.
Yeah, that makes a lot of sense. What do you do if you don't yet know how the data will be used? I would hope that data scientists would try to formulate how data should be used before it's collected. But I know that's not always the case. So what would be the approach if you don't know how the data will be used?
Well, this goes back to the process we were describing before. The reason why we spent a lot of time working on having a process that gets people to good outcomes and to solve their data publication problems is because that initial assess stage to understand the requirements better is really going to make a huge difference in how happy people are going to be with the results. If you don't know how the data will be used, it's very hard to know what to optimize for. And a little bit like machine learning has all of these parameters you need to fine-tune to get a good model in the end. Differential privacy requires often some manual optimization to get to exactly the utility requirements you need. The more vague these utility requirements are, the more likely you are to discover too late that maybe the data is not good enough for what you want it to do. All hope is not lost if you don't know in advance exactly what the data is going to be used for. There are some techniques that allow you to generate sort of either synthetic data or statistics that are good enough to answer a large range of possible queries. But in general, there's a trade-off between how much flexibility and how much different unknown use cases you want to be able to tackle with the published data, and how well you're going to be able to tackle each one of these use cases. This trade-off between utility on very specific tasks and number of tasks that you can possibly answer is not just with differential privacy. It's a fundamental privacy result that says that if you can answer precisely too many different types of queries, then it also means that you can reconstruct the data and actually have catastrophic privacy loss on the input. So basically, differential privacy allows you to quantify that and to make sure you're not releasing too much. That trade-off means that the most the most precise and explicit you can be about your success metrics, the better off you'll be with the deployed strategy.
That makes a lot of sense. It also aligns with, kind of the mantra that privacy folks have been saying for a long time of like, don't share data or basically manipulate data without first understanding what you're going to be doing, why, what it's purpose driven, really, right?
It's also in regulation, right? GDPR
Yes.
has this whole thing about purpose limitation and understanding what the data will be used for, the fact that it's going to be good to help you with your strategy. It's also going to make your compliance story like much more rock solid because you know what you're optimizing for and what problem you're solving and why you're processing that data.
Absolutely. Just a major tenet of like privacy. Absolutely. So I know that there's an example of Tumult Labs having worked with the IRS with deploying differential privacy. Can you tell us a little bit about that use case?
For sure, yeah. So the use case we help the IRS with is called the college scorecards. So the goal of this data release is to help the Department of Education in the US understand and give public information about the earnings of students who graduate from certain degrees in certain schools. So what they do is they join the data from Department of Education that has data about which students go to which degree with the IRS data that has obviously very sensitive data about the taxes and like the income that people declare. And they join these two data sets together and then publish differential private statistics on that data to allow people to get an idea of how much people earn after certain degrees. All of that data is now published online on a website called the College Scorecards. We can also add the link in the description. And yeah, that was generated using technology that we developed. One interesting thing that I find sort of fascinating about that use case is that what we hear from these customers, from the IRS and Department of Education, is that the value we provided during that engagement was not just being able to publish more statistics with better privacy guarantees, which is typically something we achieve with differential privacy, but also that it made a lot of trade-offs much more quantifiable, much more tangible.
Oh.
Before using differential privacy for these use cases, there used to be dozens and dozens of email exchanges between the two government agencies, one of them wanting more data from the other, and the other not being quite sure how to juggle the need for the Department of Education to get better data with, obviously the very strong regulation that regulate the IRS and forbid them from revealing individual information. So before that, there was lots and lots of endless discussions that it was very hard to quantify the risk or to understand the value, because when you're not using anything formal to define privacy, you can't understand the additional risk of being a little more precise, drilling down one more dimension on the statistics you're releasing, and so on. Differential privacy makes all these explicit, so it makes the process of choosing a trade-off that works for everybody much smoother and much faster.
Thank you for that. That's really compelling example and just really illustrates the benefits of this technology. So sometimes deployments of differential privacy have vulnerabilities susceptible to exploitation, based on what I understand. Can you tell us about some of the challenges here? What does vulnerability mean in this context as opposed to like a security context? And then what approaches should data scientists take to avoid these vulns?
Right. So as I was saying earlier, we're developing a platform called Tumult Analytics that allows these deployments of differential privacy. And in developing this platform, we learned that there's a few very difficult engineering challenges that emerge when trying to sort of take the results from the scientific literature on differential privacy and make them into a really neat software package. One of these issues is security. It turns out that if you have a discrete probability background, you can probably open a textbook about differential privacy, go read my blog, and understand the basic math behind the technique. It looks simple on the outside. The basic techniques are very simple. The one comparison I like a lot is the same. If you know a little bit of math and you want to understand how cryptography works, you can understand the RSA algorithm like fairly simply. It's not rocket science, right? It's not complicated. However, when you take these things and you bring them down to the level of code, it's much, much, much more difficult to get this right than you'd expect. In the cryptographic community, there's things like timing attacks or all sorts of different software vulnerabilities that can make your perfect paper, the perfect math in your paper, actually not translate to real guarantees in practice. And differential privacy is essentially the same. Anytime you're trying to do something complicated, it's very hard to track the security of your program, the end-to-end privacy of your program. And even the very basic primitives can have surprising vulnerabilities. So there's two things we're doing to tackle these questions specifically on security. On the primitives, one class of vulnerabilities that existed in the literature already for a while, but we discovered sort of new instances of that class of vulnerabilities. The translation from continuous math in the papers, when you say when you take a sample from a normal distribution in a scientific paper, it means that you're taking a sample with arbitrary precision. It's like a magic number that's like has infinite precision. You would need an infinite sheet of paper to write it completely. Of course, computers don't work this way. Computers are finite machines. So they translate this into a floating point value. And in that translation, in differential privacy, you can get vulnerabilities and the surprising behavior of floating points values that can lead to very subtle problems. It's hard to explain, but we have a blog post that hopefully with like diagrams that can explain it better. So there we basically developed our own algorithm that we can show to be secure against these vulnerabilities and ship that in our platform. A second class of problems I was talking about it earlier is the fact that even though the building blocks are simple, building complicated algorithms of stuff on these building blocks gets quickly intractable and very hard to understand. To grapple with that complexity, we built Tumult Analytics on top of a software foundation we call Tumult Core, which is made of very small individual components that individually are very simple and very easy to audit, understand, and verify that they're doing the right thing. But you can, when you assemble these building blocks together, you get an end-to-end privacy proof that only depends on the validity of each individual components. And so this modularity allows us to go implement very complex use cases. We're helping the US Census Bureau with data releases that are technically very, very complicated. We're not paying that complexity in terms of like lack of auditability or difficulty to understand the privacy guarantees, because all you need to do is audit the codes component by component, which, by the way, like third-party auditors have done for our code, and we got very positive feedback about that approach to software safety.
Excellent. Where do you recommend that listeners of the Shifting Privacy Left podcast should go to learn more about differential privacy? Are there communities or standards organizations or conferences that they should know about?
One of the things we did when we published that open source library in Python last December is it goes along a series of tutorials that explain how to use it and how to generate the first differential privacy statistics. If you're like, we wrote it thinking that our idealized user was somebody with prior experience with data analysis. They know how to use Python. Maybe they've used Pandas or NumPy or Spark, but they know nothing about differential privacy. And we woke them with like very practical examples and scenarios, code that you can copy and paste and modify about how you actually make a certain data publication differentially private. So I think it's a pretty good resource. And so I would encourage people to try and check this out, especially if the way you learn best is by by actually running some code and modifying the code and seeing how it works. If you're doing this, then also join our Slack, because we're here and we can answer questions, and we always love to get feedback on both the platform and the onboarding experience of the software library. If you're more interested into understanding how it works on more of an abstract basis, or like understanding more about the guarantees it provides, I have a blog post series on my personal website that also sort of walks you through the basics of differential privacy and assumes very little technical knowledge. So I've written it in mind with the idea of like, you know what a probability is, but that's pretty much all you need to really sort of figure out how this stuff works. So also we can add a link to that, and I can send that link.
Excellent.
You're asking specifically about communities and standards and conferences, and those are things that don't really like have a super strong existence right now, because differential privacy is still a very new and nascent field. There's been talks in the community about doing some standardization. I know there's some efforts along these lines at NIST. But it's very much sort of early days of that. I don't know about communities. We opened the Slack channel 2 months ago, but it's sort of very new and nascent, but you're welcome to join and sort of ask any questions about your use cases. Yeah, conferences, most conferences I know of are mostly academic. I had the pleasure to participate to the Data Privacy Week last month, where I think I met you, Deborah.
Yes, yeah, at the Rise of Privacy Tech's Data Privacy Week event.
That's right.
Yeah,
that's a nice place to meet people who work in the space and learn from us. And
I agree. Thanks for plugging that one. Oh, okay. So my last question to you is, how do you see this space evolving in 5-10 years? I know that's far off, but maybe that's too far off. Maybe you want to do 2 years, but what's next in the evolution of differential privacy?
Right. So I'll answer the long-term question first, because I am going to go back to the comparison I had earlier with cryptography.
Okay.
20, 25 years ago, cryptographers in academia were starting to lay the sort of formal foundations of the science, right? They were starting to make the case that if you want to deploy cryptography, you need to have formal proofs that your algorithms are solid. You need to have proofs that show very strong security guarantees. You need to have a layer of mathematical grounding to have below everything, and you need to have trusted implementations made by experts, maintained by experts that a large number of people use. And at the time, when they were trying to bang that drum, the industry, a significant fraction of the industry was like, this HTTPS thing looks complicated. I'm not really doing anything sensitive on my website. I probably don't need that. Or, people were rolling out their own cryptographic thing, and they were saying, I can't see a problem with this. It looks decent to me. And 25 years ago, it was kind of normal to hear these kind of arguments. Obviously, nowadays, we know this is nonsense. Right? We know you need to have guarantees about what you're doing. We know we need secure implementations that are well maintained, because getting this stuff right is complicated. And you know that the hand-wavy way of doing security just doesn't cut it. I think we're at the stage today in safe data publishing and differential privacy we're in a similar place that cryptography was all this time ago. We still have to bang that drum to tell people, no, if you remove the names and identifiers from a data set, that doesn't mean it's safe. No, because you came up with like a clever way of maybe adding some like randomness here or there, or generalizing some of the attributes, you're doing privacy right. Like, no, if you take any PhD student and you ask them to break your stuff, they will probably break your stuff in a matter of weeks, right? But this has not yet permeated completely the industry. It's still an acceptable thing to do to not use any formal guarantees. My hope, to answer your initial question, was that in 10 years that has changed, and it becomes sort of normal for people to rely on strong provable guarantees when they want to achieve a high level of privacy guarantees. So that's the long term, and I hope we can sort of get there. Yeah.
I think you're right. I think this is kind of the rise of privacy assurance and guarantees.
I also want to add one thing, because when you ask how do you see differential privacy evolving, I also think about what we're doing right now to get into that direction. And I think the number one thing that we're trying heavily to invest in right now, and what the field needs, is usability. Today, if you want to deploy, if you start from zero and you want to deploy a differential privacy algorithm, it's still pretty complicated, right? Up until a few months ago, I think the existing open source tools out there were sort of meant for experts and very hard to use. We're trying to change this, but it's obviously not a flip of a switch process. It's iterative. You're making the interface better. We're inventing new science to make it easy to have good defaults for everything and so on. We need to make tools and processes that are standardized, that are easy to use, that don't require the least amount of technical background possible, in order to put this technology in the hands of most people and to drastically increase the number of use cases. That's what we're investing on today, and so that's what I'm really excited to see the field evolving in the very near future, hopefully, a couple of years.
Yeah, I think so too. I think a few years you'll have more of that abstraction layer and just make it, not that you're pressing just a button, but you put in certain parameters and then, kind of press a button and the guarantees are there, right? Exactly. So making it more usable makes a lot of sense. And I think a lot of training too, right? Those who use differential privacy are typically data scientists. So I know privacy is kind of a new vertical for them to think about and might not really have understood what is involved in privacy until learning about these new techniques and systemizing that into their workflow. So makes a lot of sense. Anything else before we close for today?
No, I think it was a great discussion. Thank you so much for the fantastic questions, Deborah. It was great.
Oh, I'm so glad you had a good time. I did as well. Thank you for joining us today on Shifting Privacy Left to discuss differential privacy techniques, vulnerabilities, and where to plug into the community. Until next Tuesday, everyone, when we'll be back with engaging content and another great guest. Thanks for joining us this week on Shifting Privacy Left. Make sure to visit our website, shiftingprivacyleft.com, where you can subscribe to updates so you'll never miss a show. While you're at it, if you found this episode valuable, go ahead and share it with a friend. And if you're an engineer who cares passionately about privacy, check out Privado, the developer-friendly privacy platform and sponsor of this show. To learn more, go to privado.ai. Be sure to tune in next Tuesday for a new episode. Bye for now.